All right, perfect.
Okay.
Well, welcome everyone. We've got today's talk on development and testing of prototype Sabatier reactor for Martian in-situ propellant production. Speaking today, we have Andrew Zlindra et al. From the UBC Mars colony. Welcome, and floor is yours.
All right, thank you very much. Yeah, I'm on mute. That's good. So, hi guys. My name is Yash. I'm part of the UBC Mars colony design team based in the University of British Columbia in Vancouver. And Andrew Zlindra is one of our leads on the team, and it's his name on the paper, I guess. So let's get right into it. So who are we, first of all? UBC Mars Colony is a student-led engineering design team that's been around since 2016. We're dedicated to answering the question as to what's going to happen that when we get to Mars. There's a lot of efforts being made to get to Mars right now. You know, Elon Musk is at the forefront of that now with Starship. NASA is also eventually has plans to send humans to Mars by 2030, 2040, if I'm not mistaken. And so everyone's really concerned with getting to Mars right now. Our question, the way this team was born, of the question that what are we going to do once we get there? How are we going to make things sustainable for an eventual base on there to sustain human life? And that's kind of what our goal with every project on this team is. So that's a photo of our team from 2019, last year. And we're located in Canada, University of British Columbia. We're based out of there in Vancouver. So this is what our organization looks like, just to give you a bit of context as to how things work in this team. We have the captain, Garnet, and we have the support team. Mars Farming is another new project that we've just started this year to kind of figure out a source of sustenance on Mars for a long base. It's a pretty exciting project. Not something we'll be getting into today, but maybe we can discuss that later if you like. And the Sabatier fuel plant team, which is this project. I'm the project manager for that. And we have our 4 separate sub-teams. We have the electrical sub-team with our 3 co-leads, and fuel plant design team, process and chemistry team, and the test reactor team, which is Andrew's, whose name is on the paper over there. So right now we have 47 members in total on the UBC Mars Colony team, and 28 of them are dedicated to the Sabatier project as of now. So Sabatier project, the goal with this is ultimately in-situ resource utilization on Mars to produce a methyl propellant, which is the propellant of choice for the Reactor engine on the Starship that Elon Musk is currently building for a Mars trip. So the whole, everyone here is probably a Mars nut, so I'm not going to go too much into detail about the Sabatier reaction, but I'm sure it's been discussed over and over. You guys know about it. Just a quick recap, the Sabatier reaction is you take hydrogen and carbon dioxide on one end, both of which you can get from Mars. Carbon dioxide can be pumped directly from the atmosphere. Hydrogen from the splitting of water. And then you toss that into a reactor at about 400 degrees C over precious metal catalyst, and splits out methane and water. So methane, when combined in the right ratio with oxygen, about 3.5, if I'm not mistaken, 3.5 oxygen to 1 atom of methane gives you methylox. So our goal is to ultimately propose an integrated fuel plant system that would fit inside a Starship, 1 or 2, that's part of the scope of the project, finding how many modules that would require based on Starship's architecture, and go from there. So our key deliverables for this are divided into 2 phases. Phase 1 is to build a lab scale reactor at our team space at the UBC campus to characterize different catalysts, potential catalysts, and optimize the reaction parameters. Phase 2, which is well underway, Phase 2 is a full-scale design of the methane production plant with sized components and with the required flow rates to refuel Starship or Starships in one synodic period. That's 687 days. Our last deliverable is the economic mission analysis report and a business case for our proposal, which has not yet been started work on because we're still working on the other two things. So our most recent scope change involved kind of putting everything into this one cargo module here. So there's a paper, I think it was from last year's International Astronautical Congress, or maybe it was a couple of years ago, I think, when Elon Musk initially presented the designs for a Starship. And these guys, Roy Paul et al., they kind of proposed a transport version of the Starship that would be kind of emptied out to maximize the cargo space here. And we've been referencing that paper a lot. And our goal would be to utilize this pressurized cargo module for the housing and structure of the reactor and all its components. So everything would be prepared on Earth, everything would be set up, and this thing would just land there. And then, you know, you just require a couple of people to get the ball rolling, and just open up the hatch over here, and open up that hatch here, and it would start doing its thing. You know, it would leave the modules on board the Starship for fuel generation, or it would directly be plugged into the fuel tank over here, or we could have some, you know, expandable modules here that store the fuel on the surface. So all that is being considered right now for phase 2 of this project. And so for phase 1, it's been going on since April 2019 to currently. Key accomplishments are we have the test reactor, the PNID, that's been completed. A few updated versions. We've gone through a few iterations. I think we're on version 2 or 3 right now. And 75% of the test reactor competence of source work still ongoing, but we have most of the design down. Our heating tape, which is used to heat up the reactor, the test for that is complete. We finalized the model we want. Other electrical hardware has been confirmed too. The GUI, the interface with the reactor, and the data collection systems have been almost figured out. The gas flow calculations are complete. What kind of flow rates are we expecting? What kind of production rates are we kind of working with here on a small scale? And the system's been modeled in Aspen, and a process flow diagram's also been completed. So a lot's been completed for phase 1. And so that's our latest PNID of the system. And we have like a gas prep area here. We have the reactor section here. We have a gas cooling to cool down things before analysis here. And that's basically the breakdown here of what our system's going to look like for the test reactor. So we have the 4 lines for hydrogen, argon, which is our inert gas. We have carbon dioxide and methane eventually to kind of test a reflow, how the system reacts with methane in the input as it is. So materials and construction. So we're using stainless steel tubing for this, 1/4-inch outer diameter, and everything is mounted on the frame here, all the reactor components. So the main reactor body would go in there, and the mass flow controllers over here, and the gas line would be fed inside here through the mass controllers up here, through the reactor condenser up here, and like down there, it would be like a column structure. So everything's being fit on this frame basically. So it's a steel frame, nothing fancy there. And compression fittings are Swagelok industry standard, and Hilok also an industry standard, but slightly more inexpensive than Swagelok. So that's our MFCs we're using for gas flow regulation. And that's an initial prototype of the reactor body where the catalyst and everything would be packed in here. This has now been turned into a preheat section after experimentation, and our reactor is actually going to be a lot shorter. So some more pictures here from the project. This is some of the components mounted on the frame here with, clamps and zip ties and whatnot. We have some relief valves here for the gas lines. That's the frame. It's pretty decently sized. I'd say about 1.5 meters tall, and not 1.5 meters, meter maybe, yeah. And that's kind of our in one of our members' garages. That's the preheat section of the reactor, what I just showed you before, wrapped in the heating tape and kind of covered in rock wool insulation. That's what we're using to maintain the temperature of the reactor there. And let's see, we have two primary hardware control components for the reactor, which are the mass flow controllers, which control the rate of the gas flow into the system, and the heating tape controller, which controls, it's a hysteresis controller, and we can kind of adjust the temperature precisely based on the readings from the temperature data we get. So we're collecting pressure data all across the system, temperature, and the water weight in the end, which will be used to kind of figure out the extent of the reaction and thus the methane produced, because we'll be just burning off the methane after we separate it from the water in the cooling section of the reactor. And this is a quick schematic of the process control, how we're doing it for this. We have a computer, it's connected to the microcontroller here, and that's getting input from all the thermocouples across the reactor and the mass flow controllers too. And those are ultimately really the controlling parameters for the reactor. And the reactor's output, the methane storage and scale is also recorded, and the controller here to figure out everything that's going on. And this is a kind of a preview of the graphical user interface for the reactor. We have like a notebook here showing updates, start, stop reactor, and kind of graphs, a couple of graphs that we can switch around to show the most relevant information that the process and chemistry team think it needs to figure out for the reaction. And for phase 2, which is the full-scale design and the economic analysis, that's also been going on. That started slightly later because there was a lot of research going on in that summer period where phase 1 started taking place, and it's still going on. So our key accomplishments as of September 2020 for this phase were we've established flow rates for the required production targets we've set for one Starship. We've kind of conducted simulations to figure out what we'll need with different fuel ratios and different purities of the components we're looking for. So all that's kind of been done. We've run a lot of different numbers there. We've got some solid feedback from the system. We've completed a full component diagram. That's gone through a lot more iterations. That's like the third version. I'm not going to bulk you down to the details here. But our first version that was made by Kyle Markey, our founder, he's currently doing his master's at University of Colorado in Boulder. He proposed this Sabatier fuel plant that was posted to Reddit, and it caught someone's eye, and they posted it, and Elon Musk approves too. It's like, yeah, it looks about right. So I think we're on the right track with this, and yeah, we've taken a lot of inspiration from this, from Kyle's diagram, and we built our third iteration recently, like I just showed you in the previous slide. And so this is what the second phase electrical design is going to look like. So we will have a central control system, which will be the first Starship to land really, and that has the user interface and the central control system. And eventually, when the system expands to many modules to expand capacity, each of them would have a reactor of its own, a control system, a low-level control system, and an interface panel. So some of the individual reactor hardware components we have here are the PCB, the control board, the mass flow controllers for each gas, the pressure sensors, the weight sensors, and the wireless communication module. This is obviously going to expand, but it's based on what we have right now for the test reactor that we're kind of basing this off. So the central control system is kind of at the center of that and controls everything. The graphical user interface is located here. It moderates the communication protocols across the reactor, other reactor modules. And for each of the reactor modules itself, there are certain low-level processes that are going to happen locally. Collects data, checks if there are any emergency conditions, and transmits information back to the central control system that kind of moderates everything and figures out what to tell the other reactors. And for future plans, phase one, our next few goals, immediate goals, are to integrate the test reactor into the team space on campus after it's been fully assembled. Unattended experiments, that's our next goal. Catalyst characterization, we've ordered a few different catalysts. We just haven't got a chance to put that in and test it yet. Phase two would be this full-scale subsystem design, which is already underway. A full-size component sizing and placement within the cargo module, how would all the components we've described in our diagram fit into that Starship module 1 or 2, how many would it take? And we want to do kind of analysis, mass analysis for this proposed design. Like, will it be steady? How will it stand up? And like, will it actually be able to fit in there and without tipping the rocket over itself? So this is kind of our timeline. So we're here. We started in term 1. We just started recently. We started back again after the summer. And this is our timeline here. So our test reactor is going to be ending, phase is going to be ending in ASE conference. That would be the culmination of this, where we've been accepted to this. We will be presenting next year. The fuel plant and Mars farming, both those projects we'll be applying to for IAC Dubai for next year, 2021. And there's another conference also that we're attending, slipped my mind. But yes, the International Space Development Conference, that's also another conference we'll be applying to. I just wanted to, that's the end of my presentation here. I just wanted to give a shout out to our sponsors, without whom this project would not be possible. We get a lot of funding from the university itself through professional programs there, and we have external sponsors too who help us with services in kind or money, whatever. We always appreciate it. And Aalborg, our MFCs, were also calibrated free of charge by Aalborg, the company that makes the MFCs. So they've been of great help, and this project wouldn't be possible without all these people over here. Yeah, I will take questions now. Okay, any questions in the chat? Okay, let's see. Instead of burning off methane, what about using it as a heat source in the HAB units? And for hydrogen, are you looking at ways to store it for later conversion to fuel? Yeah, so when I say burning off methane, I'm just talking about the test reactor, because this is all inside a building. It's going to be inside a fume hood. We don't really want to be storing that methane anywhere. So we've determined that the safest thing for us as a student team is to just burn it off, because we're producing very little amounts. But eventually, that methane is really going to be cooled down and stored and combined with oxygen to get the metalox propellant. So that's a part of the phase 2 that we're working towards. Yeah, good question. Yeah, exactly. Someone already answered that. I didn't see that. Thanks, Patrick. How would you expand your reactor for industrial operations? Yeah, so the whole goal with this is to make it, and for the first, depending on spaceships, SpaceX's mission architecture, our whole project is kind of based around that. So as more details are revealed on that, I think Elon Musk is speaking later, actually. I will be tuning into that, and we will be trying to figure out what they're doing and kind of make our business plan suited to theirs. And so everything would fit in one Starship, ideally, the way I think things are going right now. And eventually we can have multiple starships with multiple modules, and eventually we can specialize modules like only reactor and a central control system. So the more starships land, the more reactor modules you have, basically. And you could expand that and eventually connect up the starships and make them like a stationary, your initial plant, until you can get things rolling on the ground and build an actual structure, which may take a lot more infrastructure. Next one, how many entities or companies do you reckon are working on Mars? I would say not a lot. A lot of people are focused on getting to Mars, which is a huge challenge in itself. But we've definitely seen some academia before that we've referenced, like the Roy Paul paper that proposed basically a chemical plant on Mars from way back in 2016. What kind of methods are you considering for farming? I'm going to address that later. Maybe we can talk later because that's not related to what's going on right now. Do you anticipate having a prototype ready for the 22 transfer window? Our goal is to finish proposing the whole structure and what would go in it by the conference. So whenever that is, hopefully it's before the 22 window. Why does the system need to be in a pressurized compartment to travel to Mars? We decided that it's way easier to control things inside the pressurized environment of the Starship, because that's already a given. You know, it's going to be pressurized inside, instead of pulling everything out and requiring all that extra manpower and setup and dealing with the Mars dust and the other conditions. Everything is regulated inside, and that's why we decided to stick with everything inside. You know, it's so much more convenient. Should aerogel replace rock wool for lighter insulation? Yeah, possibly. We're just working with what we have, because it's just a lab scale reactor for now. We're not really concerned. We just want to get the job done as cheap as possible. So how will these reactors be constructed? Everything will be prefabbed on Earth, basically. Can you talk about the inputs? So where will the pumps to draw in CO2 be located on the ship? So yeah, all that is kind of up in the air right now. We're still figuring out design strategies for that. Do we want to put this outside? Do we want to mount it in the ship somehow after we remove the fairings? Water we'll be making some recommendations on that. But mining water from Mars is a whole other ball game. Maybe a second project. There's a lot of questions. I'm going to try my best to get through all of these. How much more effort would be needed to allow it to run autonomously on the first cargo-only windows? I really don't know. It really depends on the analysis we conduct with our system design. We're going to try to make it as autonomous as possible, but I'm expecting there's going to be some level of human interaction required to get this thing up and running. A minimal skeleton crew, maybe. I'm not really sure. We'll figure out things. No, we have not reached out to Elon Musk and SpaceX. Like I said, we've been mentioned on Twitter, but we want to kind of have this plan in place, I think, before reaching out to him. But yeah, it would be really cool to work with SpaceX and know more. I think being a Canadian team has also contributed to some of the troubles we face in terms of competitions and talking to a lot of people in the US. That's been one of the challenges. Have you considered integrating with the that would be the dream if we get some space in Boca Chica, but yeah, if classes would allow us to, I would definitely love to go. We're all full-time students. Keep in mind, while we're working on this project on weekends mostly. So every Saturday we have meetings, and we work during the week too. Sorry, did I hear someone with a question? Or, how will I test CO2 pumping from Mars-like atmosphere? That's a good question. We're going to rely on a lot of NASA studies that have been done already, and we'll see how it goes from there. I don't have any concrete plans. If we have the time to get a prototype running, yeah, sure. I would imagine there's a lot more testing to be done. Like we don't have those kind of environmental chambers or facilities to really test that. So we will be working with what we have, the theory, and we'll let other people with the right resources take it from there. How is maintenance handled? How long can the system last? Yeah, it really depends. I'm imagining like the catalyst will be the thing that really needs to be replaced. So that's another thing we're looking at with phase one. We want to see whether we can recycle the catalyst or somehow unplug the pores in the catalyst after it's been deactivated. So one technique I was thinking of is hydrogen bracketing. So there's a lot of things we're considering which we'll put into the maintenance cost eventually. But right now we're just focused on the system design itself. I think, do you think our Sabatier project is unique? I'd say we're one of the few people working on this, making it to actually produce a completely integrated system, like all in one that could work with spaceship's architecture. Our end goal with this is to make it as neatly fit as possible into SpaceX's architecture, so it's actually business viable. Challenges for receiving funding. Yeah, it is a pretty challenging looking for funding, because a lot of companies, our team is pretty unique in the sense we don't have a competition. We do a different project, like almost every 2-3 years we do a different project, and a lot of people don't get that. And it's a very cool team for sure. And a lot of people are like, oh, companies are like, yeah, that's cool, but they don't really want to just like kind of fund us. Yeah. So we've tried approaching chemical engineering companies for this specific project. We received some input, but not too much. I guess there's just not much of that here locally in Vancouver. Power consumption is another thing we'll be looking at in phase 2. Like, will we be able to run this solely off solar power, and how would we do that? Or otherwise an RTG or a Gen 4 nuclear reactor or something like that. So that's part of phase 2, calculating complete power consumption and what's going to happen there. Sorry, coming back to the project being unique. The way I see it is that it's all open design work. It's all academic. We have to release all our design work. We end up releasing it. It's all open source. And we're really building up on what people have said. Like I think we're the first, we're one of the few people who are attempting to neatly integrate this all into one, like I said before. So it's not really a competition. We're trying to build on what others and experts are kind of saying and put it all together into one package. So yeah, visit our website. I'd love to talk about the Mars farming project more. We're currently in the process of, I saw a lot of questions about that. We're currently in the process of deciding what direction it's going to take. The new members are going to be really deciding what direction it's going to take while the rest of us work on Sabatier. So I would encourage you all to visit our social media, follow us on social media, visit our website, ubcmarscolony.ca. You'll find a lot more information about there. If you want to support us, there's a page there. Just have a look and follow us on social media for updates and cool stuff from our team. We are definitely engaging our local community. That's one of the things, my responsibilities. We've been going to a lot of, we've been reaching out to high school students, doing outreach programs there in terms of space exploration, and doing activities, engaging them with engineering, talking to them about UBC engineering and a career in engineering. That's one of the very important parts of our team. Yeah, I think that's it from my side. You guys are welcome to send us an email at ubcmarscolony@gmail.com if you have any further questions or cool things you'd like answered. Otherwise, follow us on our website and social media. Thank you very much.
All right. Well, Yash, thank you for your time, and to the entire UBC team, best of luck to you.
Yeah, thank you very much. Cheers.
All right. Thank you, everyone.